Hi guys, what's the crack? So this video we're going to go over circular motion. Okay, so we're going to look at what actually is circular motion. Can we calculate what we want to know about the International Space Station? Can we calculate that force on that International Space Station? Can we calculate its angular velocity? We want to look at if we have a ball on a string, how can we calculate an expression for the tension of that spring? And let's say we've got a race car banked on a curve, can we find what the radius of that curve is? Okay, so circular motion. We know the International Space Station, right? The International Space Station is a satellite that orbits the Earth. Okay, so it orbits the Earth, it travels the whole way around the Earth. And we know the reason that the International Space Station orbits the Earth is because there's a force of gravity pulling that International Space Station towards the Earth. Okay, so that force of gravity is what keeps the International Space Station in its circular motion. So when it's circular motion and it's the force of gravity pulling that circular motion, we call that the centripetal or centripetal force. Okay, so that's that force trying to pull it towards the center of the circle. Okay, we know the satellite doesn't end up crashing into the Earth because the satellite has a speed, right? It orbits at a certain speed. So we know that the force of gravity doesn't pull that satellite towards the center of the Earth because it doesn't do any work. So gravity, it does no work on the satellite. And we know the force of gravity doesn't do any work on the satellite because the equation to calculate work done is equal to force times distance. Remember that distance has to be the parallel distance. So again, we've got a force of gravity pulling towards the center of the circle. But if the satellite was moving in that direction, then that force of gravity is doing work. That satellite is moving perpendicular to that direction. So because the satellite is moving perpendicular to the direction of the force, the satellite, that has no work done on it. That force of gravity does no work on our satellite. So what that means is the energy of the satellite doesn't change. So if the energy of the satellite doesn't change, we know that means its kinetic energy doesn't change. So what we know is that the speed of the satellite isn't changing. Okay, so what we're saying again is the gravity is the force pulling that satellite towards the center of the Earth. We call it the centripetal force. But that force of gravity doesn't do any work on the satellite because the satellite is moving perpendicular to the force. So that's why there's no work done on it. So we say then if there's no work done on it, its energy is not changing. So its kinetic energy is not changing. Remember, kinetic energy equals 1/2 of its mass times its speed squared, or the magnitude of its velocity. So if its speed is not changing, or the magnitude of its velocity is not changing, that's why it doesn't spiral and crash into the Earth. So we just said the speed is not changing. However, hopefully you can see that the velocity does change. Because as the satellite orbits the Earth, we can see that the direction changes each time. Because remember, velocity is a vector. It's got both a magnitude and a direction. Just look at our earlier videos on what vectors and scalars are if you forgot that. So again, we're saying the magnitude of the velocity, the size of the velocity is staying the same, but its direction is constantly changing. So we know our satellite is accelerating. And we know to calculate that acceleration, because acceleration is the change in velocity over time. So again, our satellite is accelerating because it is changing velocity, because its direction is constantly changing, okay? And the direction of that acceleration is towards the center of the circle, okay? So again, how we can write acceleration in circular motion is acceleration is v squared over r. So v is our linear speed, that's a velocity there, over r. R is the distance between the center of the Earth and the center of the satellite. Or we can write w squared times by r. Okay, what w stands for is actually your lowercase omega. Okay, so w stands for your orbital speed, okay, or your rotational speed. So if v is our linear speed, it's always the tangent towards the circle. That's, for example, if we were spinning a ball on a rope and the rope is a break, that's the speed that it would go off at tangent to the circle. And w is our rotational speed or our angular speed. And what your angular speed equals is the angle it goes through in a certain time. So let's say we're going to go for a full circle. A full circle is going to be equal to 2 pi radians. And if it goes through a full circle, we know the time to complete a full circle or a full oscillation is always equal to the period. So what we can write now is that the angular speed is equal to the angle it goes through over time. But because we did 2 pi radians over time, that's why the unit then is going to be in radians per second. We also know from way back in GCSEs that 1 over the period is always equal to the frequency. So another way that we can write that angular speed is 2 pi f, and that's the one that's in your data sheet or your formula sheet. Okay? So again, what we're saying is our satellite is accelerating. We know that it's accelerating towards the center of the Earth, but again, it's not being pulled towards the center of the Earth because that force of gravity is perpendicular to the direction of its motion. Okay? So again, we know we've got its linear speed and we know we have its angular speed. So now we can apply these equations to the International Space Station. So let's say we have our International Space Station and we know that it orbits in 90 minutes. Okay, so it takes 90 minutes to complete one orbit. So if it takes 90 minutes to complete one orbit, what that's given us there is that time period, the time for one orbit. But we know we don't like it in minutes, it has to be into seconds. So to get from 90 minutes into seconds, we just multiply by 60 to figure out that time period there is going to be 5,400 seconds. So that's the time it takes the International Space Station to complete one orbit. It told us the mass of the International Space Station and the radius of its orbit. So what we can calculate is we calculate what is its angular speed. Its angular speed again is going to be 2 pi, the angle it goes through, divided by the time it takes to go for that angle. So we can do 2 pi divided by the time it takes to go for that full circle was our 5,400 seconds. So now we can calculate our angular speed. So do 2 times pi on your calculator and you'll divide by 5400 to get your angular speed, which comes out at 1.16 times 10 to the negative 3. And again, our units are radians per second. So radians per second. You might be thinking, what is a radian? Okay, so a radian is just another way to define angles and circles. So we know that you've always done a circle before is 360 degrees. So 360 degrees is always equal to 2 pi radians. It's just another way to define angles in a circle. Okay, so 360 degrees is 2 pi radians. So if I want to know what 1 degree is, it's just going to equal 2 pi over 360 times radians. So you can easily convert between your degrees and your radians. Okay, so now we know what its angular speed is, we can actually calculate what is that force, what is that centripetal force on the International Space Station. And to calculate force, we know what we do is our mass times by our acceleration. But because it's moving in circular motion, what we can do then is we can use our equations here for acceleration. So acceleration is v squared over r or w squared times by r, okay? So I've just calculated what W is, so that clearly the easiest equation to use to calculate the force is going to be my W squared times R. So what I'm going to write now is my force is equal to my mass times my rotational speed squared times by the radius of its orbit. Okay. So to calculate the force, we just take the mass of our International Space Station, which is 4 times 10 to the power of 5, multiplied by our angular speed squared. We just calculated the angular speed. Is multiplied by 1.16 times 10 to the negative 3 all squared. And we're going to multiply by the radius of its orbit. Remember, the radius of its orbit is always from the center of the Earth to that center of mass of the International Space Station. And we were told that's 6.77 times 10 to the power of 3 kilometers. Be careful here, that's in kilometers. And remember, to get into meters, you have to multiply by 1,000. So we're multiplying by 6.77 times 10 to the power of 6. That's what it is in meters. So now to calculate what our force is, our centripetal force on that International Space Station, we're going to do we should do our squared bit first. We'll do 1.16 times 10 to the negative 3 squared. We're going to multiply by 6.77 times 10 to the power of 6. And we're going to multiply by 4 times 10 to the power of 5 to figure out what our force is on that satellite, and it comes out at 3.64 times 10 to the power of 6 newtons. So again, that is our centripetal force in that satellite, and we know that centripetal force is caused due to gravity. So we actually calculated was that force of gravity on our International Space Station. So again, just always double check your math. So again, what we did earlier was 2 times pi divided by 5,400 to get us 1.16 times 10 to the negative 3 radians per second. And then all we did was we took that number squared, we multiplied by our radius, which was 6.77 times 10 to the power of 3, multiplied by 1,000 to get it into meters. And we also multiplied by the mass, which it told us was 4 times 10 to the power of 5. And we get our 3.64 times 10 to the power of 6 newtons. Okay, so other things you might have to do then is that you might have to think about a ball on a string. So you know if you've got a ball on a string and you're rotating that swing or swinging around that ball, we know that there's going to be 2 forces acting that ball. You know you're going to have the force of gravity, always pulling it straight down, so that's m times g. Weight is mass times gravity. And you're also going to have a tension in your rope. Okay, so now to think, if it's circular motion, I know there's always going to be a resultant force going towards the center of the circle. So there must be a bigger, because remember resultant is a difference, there must be a bigger force going towards the center of the circle. So if I only have the force's tension in mg, that bigger force must be the tension. So my tension here is going to be my bigger force. So this arrow doesn't really make much sense because it's too big now. So I'm just going to rub it out to make it much smaller to show that the tension is the bigger force. So m times g. So what we're saying is our tension is greater than our downward force due to gravity because it's the centripetal force pulling towards the center of the circle. So what we can say now is that the tension, take away the mg, is equal to that resultant force. And we know that resultant force is a centripetal force due to gravity. So a way we can write it now is tension take away mg is equal to our resultant force. Resultant force is mass times acceleration. Because it's circular motion, we know we can write this for acceleration. So let's say we know what the linear speed is of that ball. We can write that it's mv squared over r. So if I want to write an expression for my tension, I can see that it's going to be mv squared over r, the mass of the ball times its linear speed, divided by the radius, which in this case is going to be the length of our string. And then we're going to add on the mass of the ball times by gravity, which is 9.81. Okay, last way you might see circular motion coming up is if we got, say, a car on a banked curve. Sometimes you might see an airplane on a bank curve, okay? Or an airplane going in circular motion. So imagine we've got a car on a racetrack. We know it's got 378 kilometers per hour, and I want to find the radius of its curve. So I know if that car is going in circular motion, there's going to be a force pulling towards the center of the circle, a resultant force pulling towards the center of the circle. So again, if I just model it where I've got my car on my bank curved, let's say we're at 30 degrees, I'm going to have a resultant force pulling it towards the center of that circle. So it's my resultant force. I know the only forces actually acting in this car is going to be my downward force to gravity, mg, and I'm going to have my normal contact force, which is going to act perpendicular to the surface. Okay, but what we did here, that is a misconception because it looks like I've got an extra force on it, but I don't, right? Those are the only 2 forces actually acting on my car. And we know then that when we resolve these forces, one of the components is going to end up giving us what that centripetal force is going towards the center of that circle. Okay? A misconception is people trying to do this as the centripetal force. But that's not the center of the circle because in a bank curve, it's going in an angle, the center of that bank curve. So that's why it's always going towards the center there. So clearly what we can do is we can resolve to figure out what component here is causing that centripetal force. The weight is exactly perpendicular to that centripetal force. So there's not going to be the weight. It must be because of that normal force. So we can resolve that normal force into its vertical and its horizontal components. So I can see here that the horizontal component of that normal contact force is what's causing that centripetal force. So I need to find what the angle is. So I know there's 30. So there is my equal angles. So that angle in there is also going to be equal to 30. Okay, because that's Z shape. So I can see there's my 90 degrees. That's going 90 minus 30. So this angle in here is also going to be my 30. And remember, physics, you always want quick rules. If you go through the angle, it's always cosine. So that vertical component there is going to be n cosine of 30 going through the angle. And this horizontal component here is going to end up being n sine of 30, okay? So what we're saying now is that horizontal component of the normal contact force, that n sine of 30, that equals our resultant force pulling towards the center of the circle. And that resultant force pulling towards the center of the circle is our circular motion. So what we can write now is n sine of 30 is equal to mv squared over r. And the reason we're using mv squared over r, because remember resultant force is mass times acceleration, mass times acceleration. The reason we're using the v squared over r this time instead of w squared times by r is because we were given what its speed was, what its linear speed was. So I know that n sine 30 is mv squared over r. I can see that n cosine 30 must be equal to mg because up equals down. And then hopefully now you can see I can insert one of these equations into the other or simplify. Because I know my general maths rule is that anytime I have a sine theta divided by a cosine theta, we always get a tan theta. So what I can do here is that my sine theta divided by my cosine theta. So n divided by n just cancels. Sine theta over cosine theta gives me tan of theta, so tan of 30 equals, I'm doing this divided by this, so my two masses are going to cancel. So what we have is we're going to have v squared over r times g. So we did v squared over r divided by g, so multiplied by 1 over g. So if I want to calculate now what the radius is, clearly we can see if I want to calculate the radius, what we're going to have to do is we're going to have to do our v squared divided by g times by tan of 30. So we just rearrange this now. So r times g times tan 30 is v squared. So r is v squared over g tan 30. And g, we know to use on Earth, is always going to be 9.81. We are also given v, okay? But careful here, we'll give it in kilometers per hour. So it's 378 kilometers per hour. So I have 378 kilometers per hour. That's 378 times 10 to the power of 3 meters in 1 hour. But I want to get into meters per second. So if it goes that many meters in 1 hour, see how many meters it goes in a second, we'll divide by 60 to see how many meters it goes in a minute, and divide by 60 to see how many meters it goes in a second. So what we're going to do now is we'll do 378 times 10 to the power of 3 to get in meters per hour. We'll divide by 60 to get it in meters per minute, and divide it by 60 again to get into meters per second, which is 105. So what we have is that's going to equal 105 meters per second. So now I can slot that in here to be 105 squared. So now I calculate what my radius of that bank is. So what we're going to do is 105 squared, and we're going to divide by 9.81 multiplied by the tan of 30. And we get our radius, that radius of that curve, to be 1946.6. meters. Okay, so again, just double check your math all the time because it was a lot of time in your calculator. So again, what we did was our 378 times 10 to the power of 3 to get into meters per hour, divided by 60 to get it in meters per minute, divided by 60 to get it in meters per second. What we had to do was square that number. Then we had to divide it by 9.81, and then we had to divide it by the tan of 30. And we get 1948 this time I got, but again, it must be because of rounding. So 1948.6. I was going to double check it because I wrote 6. So again, what we're doing is 105 squared. We're dividing by 9.81, and then we're going to divide by the tan of 30 to get 1946.6. I'm not sure what I typed in there the second time. But yeah, always double check your calculator. So hopefully that was useful.